Hi guys, in this video we will begin looking at simple additions to carbonyls and nitriles. Simple addition as opposed to addition elimination. Alright, we'll see what that means. But we'll also start bringing in reactions with aldehydes and ketones at this point. Now this warm-up question here, question number 1, what reagent would react with compound A to give the drug tramadol? This is indeed an example of a simple addition, but we also need to be able to sort of see what's going on here and to envision what type of reagent would be used to accomplish this reaction. Okay, also, final exam is comprehensive. Another question could be, can you show 4 different products that could be obtained from the reaction of tramadol with HBr? So also give that a try. Okay, simple additions. We'll also have new reagents. And I'll go through this material using this approach here with these different line reactions which illustrate the different reactions. Number 1, it's actually acetophenone. It's a ketone. If we reacted with sodium borohydride or lithium aluminum hydride, what product do we expect? All right, we need to know what these reagents are. Now, we use sodium borohydride in organic 1. It was the second step of the oxymercuration reaction, starting with an alkene. And we did mention in organic 1 that it is a hydride source, H-. It reacts as if it's a hydride source. All right. Now let's talk about these 2 reagents a little bit first before we look at any chemistry or mechanism. Sodium borohydride, the boron has 4 bonds to H's. And because boron should only have 3 valence electrons, it's group 3, it has 4 here, it is a minus. If you got a minus, you got to have a plus, and the plus is sodium. And so this can be written as NaBH4. But the boron is not happy. It's actually hard to make boron happy. It's minus here. It doesn't like being minus. It's even less electronegative than carbon. And so it tells the H and the 2 electrons, hey, take a hike. And the H nucleus and the 2 electrons. And if you consider the H nucleus and the 2 electrons, we can consider something like that. And that's a minus. So the boron is like it told this H and 2 electrons to take a hike. Well, the H and 2 electrons, the 2 electrons can go and react with something else. It's almost like a sigma bond acting as a nucleophile, but we can consider it like a hydride. And the hydride here is going to be our nucleophile. It's not H+, it's H- with a lone pair. Now we also have the aluminum version. Aluminum sits below boron in the periodic table. The aluminum is also minus here. This could be sodium. With the aluminum hydride, it's called, most common you see lithium as the cation. I think we have some sodium, I'm sorry, not that. We actually have some potassium borohydride around. But with the boron here, you most commonly see sodium. With the aluminum, you most commonly see lithium. That's probably just because how it is made and the practicalities to just making this on a commercial scale. But the business end is the anion here, and just like the boron, the aluminum is mad, and it tells the H and the 2 electrons to take a hike. By the way, once this takes a hike, then you get a boron with 3 H's, or an aluminum with 3 H's. The boron's not happy there either because it doesn't have an octet. As I mentioned, it's hard to make boron happy. Now, you can also have just NaH. That is a molecule or salt that is known. This would be, of course, Na plus and H minus. All right, clearly H minus here. But we will never use this as a hydride source because it's just in practice not a good hydride source. These are better hydride sources. Now, which one is more reactive? Well, LaH. By the way, I call it LaH, lithium aluminum hydride. Okay, a lot of times it's just abbreviated as LaH, or when we say it. Okay, LaH is more reactive as a hydride source than sodium borohydride because which central atom is matter? Okay. Well, boron is more electronegative than aluminum because it's higher on the periodic table. That means boron likes negative better than aluminum. Now, neither one really likes it, but aluminum really hates it. And so it's really would like for this H and 2 electrons to take a hike. It is a stronger hydride source. All right. And there's some practical consequences of that. It also tends to be a little bit more dangerous to use. It's more prone to causing fires because if you have like water around, okay, and H minus, which this is essentially an H minus source, right? These electrons can take an H, and you will generate HH. All right, that's hydrogen gas. H2, it's flammable. The Hindenburg exploded, okay? You get this around water, hydrogen can ignite, you got a fire. Sodium borohydride also will react with water, but not as vigorously. Okay, so that's a little overview. I have a little extra time here. All right. That is a good overview for you to consider there of these 2 common hydride sources. Now back to the chemistry. We know we have a hydride source. This will act as a nucleophile. These electrons add here, electrons up, right? Nucleophilic addition to carbonyl. That's going to give, I'll just draw my benzene ring as a phenyl. Electrons up, minus, gives that there. Okay. Ah, there's a new H there, right? I didn't draw it in. If you'd like for me to draw it in, we can. There's the new H. That was our nucleophile. Very small nucleophile, right? Okay. At this point, with acid derivative chemistry, we did an addition followed by an elimination. The problem here is there is nothing to eliminate. There is no leaving group. We're not going to eliminate a plain carbon, a plain hydrogen, or a plain benzene ring. All right? Typically, you're not going to eliminate an H or a carbon. Sometimes carbon in special cases. We will point that out when we do it. Okay? Game over. This is it. This is just a simple addition with no elimination. The only thing we can do here is come in here with H plus workup and just protonate our anion here, and we will get that alcohol. Now I'm not going to draw in the new H here because it'll look funny, but it is there, right? And that's the product here. Okay. Now, water will actually supply the proton here. That's why in the directions I say assume excess reagent. By the way, even if there was excess reagent, we're only reacting once here. I also said assume aqueous workup. All right. But with aqueous workup, we're going to put the proton on to give the OH group, and that's where the H would come from the water, or you could throw in acid. All right. Now, it's also a difference. When you use sodium borohydride, product solvents are okay. So we can use like ethanol. You can even have in water, although that's not as safe as alcohol, etc. Okay. If you use LAH, no product solvents. You will have a fire because the hydride will take the H of a product solvent, make hydrogen, and it will likely ignite. But sodium borohydride will not do that. You won't have any practical problem. Okay? In some cases, if we use sodium borohydride, we can include a product solvent here. Okay? Or maybe ethanol, such as solvent, and then this can take an H from the ethanol. All right, we can talk about that more. Simple addition, we're going to get this. Now we've actually reduced, okay, all right. These are actually considered reduction of the carbonyl. Because, look at the carbon. It has 2 bonds to a more electronegative atom. Now the alcohol only has 1 bond to a more electronegative atom, the alcohol carbon. That would be a reduction. We've also added H's because the carbon got an H and the oxygen got an H. So these hydride reagents are considered reducing agents. Now if we could go backwards, if we took that alcohol we could convert it back to the ketone, and that would be an oxidation. And we covered that during test 1, and a reagent such as chromium trioxide and aqueous acetic acid or something, right? I actually think I showed this on the next page. Well, let me show you this first. I'll show an example on the next page. All right. Well, what we just did is we went to here using sodium borohydride or LAH, we will see. In the case of sodium borohydride, we could use maybe ethanol as solvent, and the ethanol would supply the proton to the oxygen anion. All right. Well, if you did it with LAH, you would want to use LAH by itself, maybe a non-protic solvent such as diethyl ether. Then you need to come in with H plus workup. Because you don't want to be mixing your LAH with a protic solvent. It has to be two separate steps, where again, it's okay to mix sodium borohydride with a protic solvent, proton source. All right, so we got this redox cycle. This would be oxidation, this would be reduction. In reduction, we often put an H in parentheses. Okay, you may think we would put maybe a RED or something. Oxidation, reduction. And that cycle is actually shown over here as a biochemical redox cycle. Estradiol, we oxidize the alcohol to the carbonyl, and then the carbonyl can be reduced back to the alcohol. All right. Let's talk about these details a little bit later. We don't use any chromium trioxide or LAH in the body. The body has enzymes that will do that. Let's get back to the chemistry here. All right. By the way, for number one, what reagent would convert product back to starting material? Ah, we just answered that, right? One of the big three. That's a test one reaction. All right. Okay, we have an aldehyde. We have an H minus source, either one of these. These electrons add here, electrons up, doop, 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 electrons up, becomes minus. The aldehyde H, the new H, that carbon has two H's. All right, we assume aqueous workup. It's going to supply the proton or H plus. Either way, we will get boom, 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 and boom. All right, there's your product. Now I drew the OH down by purpose because I wanted you to see it differently. You could draw it up if you want, down it doesn't matter. So why not just draw it zigzag? 3 carbons, and then the 4th carbon now has 2 H's on it, right? There's 2 H's there, and then the OH. So we can reduce our aldehyde to the primary alcohol. If we want to go back, what reagent would convert product back to the aldehyde? Well, you wouldn't want to use one of the big three because that would take the aldehyde all the way to the carboxylic acid. You would want to use, do you remember, the Tollens reagent. That would stop at the aldehyde. Okay, let's try the next one. Grignard reagent. We know this is essentially a benzene ring with one of the carbons being an anion. All right, of course, you got to make sure you know the structure. One of the carbons is an anion. But this is our nucleophile, nucleophilic addition to carbonyl, electrons up. That's going to give boom, 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 electrons up. Got the original aldehyde H and now a benzene ring. This mechanism is no different. The only difference is different nucleophile. And if we somehow supply a proton, we will get boom, 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 boom. I'm going to draw the phenyl there, and I'll draw the OH like that, and there you go. And we just made this bond by a simple addition of the Grignard reagent to the carbonyl carbon, electrons up. Nucleophile carbon OH. Nucleophile carbon OH. The carbon OH used to be the carbonyl. If you remember when we were doing epoxide chemistry, we had nucleophile carbon carbon OH as products. All right. For product 1 and 3, is the product R or S? Good question. Because these products here, 1 and 3, the carbonyl carbon becomes a chiral tetrahedral carbon. R or S? Okay. Well, it would be racemic. That's because essentially when you add to carbonyl, it's sort of flat. If we add from the front, actually we always do this on the board. It's actually known that the nucleophile actually adds sort of like this. All right. And the nucleophile, if it comes from the front, it would be forward, and it will push that oxygen back. Let's make this chiral. That's not chiral right there, but now it is. All right. But this can either be kind of from the front or back. It can also come in from the back. If it came in from the back, this is nucleophile. Nucleophile, it would push the oxygen forward. Okay? And since the original is planar, you have a 50-50 chance of being on either side of that. You're going to get both. You're going to get a racemic outcome if the carbon becomes chiral. Okay? In the second reaction, the carbon does not become chiral because, well, there's two H's on it. Okay. At this point, we can think about synthesis. How would you make these products? What starting materials would you use? Okay, I can just give you another product here. Working backwards is important too. The compound below, there are 3 different groups bonded to the alpha carbon. The alpha carbon is the carbon bonded to the oxygen. The first carbon bonded to the oxygen. Show 3 different addition reactions that would give the following compound. All right. Addition reactions to a carbonyl. All right. Think about that and show 3 different ones. So, those were simple additions. What if we had an acid chloride with an H- source? Let's predict product here, but let's think mechanistically. These electrons add here, electrons up. That would give that. Yeah? That's just a nucleophilic addition. All right. Up above, when we did that, the reaction stopped there. There was no leaving group. Here we have a leaving group. These electrons are not going to wait to be protonated. These electrons are going to come back down and kick off this leaving group. And that's going to reform the carbonyl. That would give an aldehyde, right? Yeah? Plus the Cl minus. Well, the aldehyde can react again, and indeed it will. Another H minus comes in here, electrons up. Now we have two H's here. So an addition, elimination, and we did another addition. All right, at this point, game over. Stops here. How about if we write game over? And now the only thing you can do is just have an H plus workup, and that will give that product there. This carbon has two H's, and we will protonate the oxygen. All right. In this case, the LAH, the hydride from the LAH, is going to add twice. Because after the first addition, we reform a carbonyl by expelling the leaving group, and then we add again. Overall, we converted our acid chloride into an alcohol. All right. Let's don't memorize that reactions of acid chlorides with two equivalents of LAH give alcohols. Please don't memorize that. Please just think mechanistically, and as you work through your mechanism, eventually you'll get good enough to just recognize this in your head. Okay? Show the aldehyde. And then when it adds again, there's your product. Yeah, it happens to be a primary alcohol. Okay, what if we wanted to stop at the aldehyde? Could we do it? Well, you actually can. Diol H is what is considered a hindered hydride source. Okay? Diol H structure is it's an aluminum hydride. But it's not an anion. It stands for di-isobutyl aluminum hydride. Now, you remember when we had acid chlorides and we had aluminum trichloride? That would be trigonoplanar. And our acid chloride complex with the aluminum. That may be what's going on here. If we consider these to be, okay, let's complex it here instead. we would get aluminum with diisobutyls and an H, and then that aluminum would be minus and the chlorine would be plus. Now the aluminum's mad and this hydride bond, bam, okay, maybe something like this. All right. Because the trivalent aluminum is going to be a Lewis acid. Get to here, aluminum is now an anion mad. Hydride source has been made stronger as a carbonyl. But it's okay, okay? It's okay to just show it like I did here. It's a hydride source adding to carbonyl. Same thing here. Hydride source adds, okay, eliminates, and we're going to get our aldehyde. But it stops here. Dibol. Dibol H, we can say, does stop at the aldehyde. It does not add again. Two reasons why. First off, it's done cold. The second reason possibly is that the two isobutyl groups give the reagent some steric hindrance. Okay? Not going to go into that any further. All right, Dibol H is considered a hindered hydride source. All right, let's look at next reaction is with a Grignard or an alkyl lithium. They both give the same product. And this is going to be the same as up here. The only difference is instead of a hydride adding as a nucleophile, we have an ethyl group. You can work through the mechanism. I'm just going to show it as above. That is, after at the sort of intermediate stage, instead of an H on the carbonyl, we're going to have an ethyl. All right, so it's not an aldehyde, it's actually a ketone. But then with another ethyl, okay, I'll show another ethyl. You can do it over here, same thing. When the other ethyl comes in, all right, and I'm going to go ahead and show the H plus workup just to save room. We would get before workup this would be minus, but with workup I'm going to protonate it, it become neutral. Hold on now, that's an ethyl, but we would have another ethyl here, right? And we just made this bond here, nucleophile carbon OH, and lo and behold, that's a tertiary alcohol. Nothing to memorize. All right. Right? Of course, back over here we had an ethyl anion. Electrons add, electrons up. All right. And then elimination of the leaving group gives your ketone, but it will add again. All right. Grignards and alkyl lithiums will add twice. That is, they will add again to the carbonyl intermediate. Which is usually a ketone. Now, what if we wanted to stop at the ketone, like we stopped at the aldehyde? There is a reagent to use. It's called an organocuprate. All right. All right. This ethyl is going to be, all right. Let's look at the structure of an organocuprate. Copper. All right. It's bonded to two alkyls. All right. I'll put and it's a negative. And then you're going to have a lithium positive. Most often it's lithium. Well, this is kind of a lot like the borohydrides. The copper doesn't like being minus, and so it tells this carbon to take a hike. And when it takes a hike, that is basically your carbanion. In this case, with it being ethyl, it's the carbon and the two electrons. Okay. The negative copper shoots off these carbanions, and they act as nucleophiles. All right. Let's see, how do you make organocuprates? They are made from like copper bromide. It's copper 2, okay? Is that right, or is it copper 1? Let's see here. Haven't thought about this in a while. It's usually on one of my handouts. Gotta be copper 1. Copper 1, I think. Yeah, that's how we get to the minus. Plus 1, negative 1. Copper plus, and then you react it with an alkyl. Actually, you can use a Grignard or an alkyl lithium. Okay. This is essentially, right, that lithium plus. These add to the copper. That's going to give a copper with one ethyl. The copper would then be neutral. Okay, you need two equivalents of this. Another one adds, okay, I'll just repeat. Second one adds, that's going to give copper with two ethyls. The copper should now be minus. All right. The lithium should sit there. All right. Since we use two of these organolithiums, there should be another lithium. We also have a Br here. And so lithium bromide would be a byproduct here. All right. Probably very strange to see something like copper with organics bonded to it, but you can. It's called an organometallic. More specifically, an organocuprate. Cuprate is when the copper is an anion. It's got the two organic groups, and these organocuprates act as alkyl nucleophiles, just like a Grignard or organolithium, but they're less reactive. Okay? All right. The ethyl anion here is less reactive than it is above. Not going to go into why. Maybe it's pretty straightforward. I'm not going to take the time. These organocuprates, by the way, are also called Gilman reagents. By the way, right here is copper 1, copper iodide. In my example, I use copper 1 bromide. Either one would be fine. And if you use an organocuprate, it will stop at the ketone, okay? And this is actually a great way to make ketones from acid chlorides, which ultimately is from, okay, anytime you see an acid chloride, you got to think of it as a carboxylic acid, because it easily comes from the carboxylic acid. So essentially you can think of it as a great way to make a ketone from a carboxylic acid, right? Now, the three reactions above, you get the same exact product if you use an ester. That is, the chloride leaves in the reactions above, okay? But also an OR group. It looks like OR. That's OR and OR. All right? If this was an ester, it would leave as well in the reactions above. So the esters give the same exact products. The thing about cuprates is esters don't react with cuprates. Only acid chlorides do, because the cuprate is less reactive. Now dibol H will react with an ester. Even though it's hindered and less reactive, it will react with an ester, but the organocuprates will not. They only react with acid chlorides. And so it's a great way to convert an acid chloride to a ketone. All right, using the Gilman reagent. All right, so we did some simple additions. Then we came back with acid derivatives and did addition elimination, followed by a simple addition. But in some cases, it will stop after just the addition elimination to give the intermediate. Okay, we'll pick up here in our next video. You can be looking ahead. I think there are some homework down here. You should actually be able to work all 4 of these already based on what we've covered. The 3 reactions at the top are a little bit specialized, okay? We'll cover those in the next video. We'll also look ahead a little bit, including, remember, think about this reaction here. What's needed to convert tramadol, or I mean compound A, into tramadol? Be a good exercise for you there. Okay guys, that ends the video here.